Hey everybody, how are we doing? It is the day of the test. So we're going to get started right here and jump into some Canvas content review of chapter number 5. Canvas content looks like the test. Let's do this. Got that energy, got that Red Bull this morning, coffee. It's actually coffee, it's not Red Bull. There will be Red Bull soon. So I'm focusing a lot on chapter 5 right now. Let me put that in the notes right here. It's basically a chapter 5 review. I can hear the music again. Sometimes I don't know what happens to my setup. I need to do everything. Chapter 5 review. So if you're watching this right now, it's probably day of the test maybe, or it's next semester, it's 10 years in the future. Who knows when you're watching it? But this is chapter 5 review. And the first thing we see right here is a normal probability plot. Now you want to memorize what this word is. You want to put it on a note card where it says normal probability plot. And you want to read it backwards to remember what normal probability plot is. It's a plot that tells you the probability a distribution is normal. Well, how does it do that? We'll go into Jump right here and take a look at a normal probability plot in Jump. We'll go over to the Diamonds dataset, and Pokemon have some good stuff. So a normal probability plot is made from quantitative data. So because quantitative data, we can look to see if it's normal. Categorical data, you don't look to see if it's normal, only quantitative with things like histograms. These are the steps which are not as important. What's more important is we're about to see a normal probability plot known in Jump as a normal quantile plot. The quantiles mean the percentages in the distribution match up to the percentages in the normal. And that line right there, that red line, we'll make this really big. That red line right there is the normal. And as in, if these points, these black dots, which are your data, you see how this black dot right there lines up to that? That's your data. That's your data down there. Notice data is really concentrated here. This is actually 50% of the data if we go from here to here. That's 50% of the observation in your data, 539, which is, yeah, almost 500 on the dot. So you can see the middle 50% is contained in the box. You can also tell the data is right skewed because the mean is actually, Jump puts a diamond where the mean is at in a box plot is above the median. So the distribution, Monster Man, we can't not draw Monster Man. If you notice, we're reviewing a lot of topics that we should know, like skew is right to the high, left to the low, whatever way the Monster Man's tail goes. And the monster's got a little bit of bimodality today, but he's got his tail towards the high side of the distribution on the carrots. And so there's a bit of outliers, there's a second modal area. People get like 1 carat diamonds and 0.5 carat diamonds very commonly, or maybe that's quarter carat diamonds too. But we see a bimodal right skewed distribution, and it does not follow the normal. And this is how a normal probability plot, which is this thing right here, tells if it's normal, is if it follows the red line. The more it follows the red line, the more normal it is. So we could see another one. We'll go to the Pokemon data, my favorite data set. I think I sent this to Moira. We go here to analyze distribution. We go to something like attack. And ooh, aside from the outliers, that looks pretty darn normal. Little right skew, Monster Man. Little right skew. More normal than the last. At this point, you might use mean and IQR, or mean and standard deviation, excuse me. Mean and standard deviation. Mean for center, because the mean's right there. It's the diamond, which is not always included in all box plots. Little bit of right skew, but Monster Man is almost a little bit symmetrical today. He's not quite, but he's more symmetric than last time. So right here, we're going to go and do the normal quantile plot. And notice it follows the line a lot better. And this one, at this point, this is pretty normal. It doesn't escape these bands, which are kind of your meh bands, like, I don't know if it really is normal. And this is what we call a diagnostic plot. You think if you go to the doctor and you get a diagnosis, this is a diagnostic plot. So all this to say, how do we determine if it's normal? We'll put this one over here with its nice looking normal-ish histogram. Even squish the normal, squish it up a little more. There, that's real squished. And then we go over here and put the other one, and we'll make it. So on the right, you see a normal probability plot that has a bend to it, doesn't follow the line, indicating non-normality. On the left, you see one that mostly follows the red line down the center. Mostly, it doesn't have to do it perfectly, and means it's normal. So all of that to do normal probability plots, and sure, I'll put this as a note, normal probability plots. And basically, once again, you want to put a normal probability plot. It's a plot that tells us the distribution is normal or not, and it does so by seeing if it follows a straight line. The line is straight, the dots are along the line. A high p-value is for a goodness of fit test. So when you see the p-value being high right here, I don't know if either of these will come back normal, but we could run a goodness of fit test here by doing continuous fit, fit normal. This will have a p-value of 0.00001, and this is called the goodness of fit test, and you see the very, very low p-values, and this is for the data that was not normal. I'll move my head here. So both these are two separate tests, the Anderson-Darling, the goodness of fit test, Shapiro-Wilk, and Anderson-Darling. There they are. There's the names of the statisticians who made them. And this is for the data that was not normal that we already decided on, and the goodness of fit test comes back with a p-value stating it's not normal. So that's how a goodness of fit test determines if something's normal or not normal. This one might come back with a slightly higher p-value, but there's topics I want to mention like power, because with this large of a sample size, I do fear we're also going to see it's not normal. It came back not normal too. How would it look if it came back normal? What I'm going to do right here is I'm going to give you one that does come back normal. I'm going to make a subset of this data and only take 25 observations. By doing this, we won't have the issue we had previously, and I think we did like attack. And see, that looks pretty darn normal. Normal probability plot's going to follow the line. See how it follows the line right there, which means we still believe it's normal. So I look at it. Looks unimodal symmetric, believe it's normal. The normal probability plot follows the line, still believe it's normal. We run a goodness of fit test to see if the normal curve is a good fit. It's called goodness of fit because you literally fit the normal curve over it. Notice how a normal curve has been fit on top of the data. It's kind of bulging out there, not working so well there. It's in a little gap right there. Not perfect, but it looks pretty good. And if it looks pretty good, when you do the p-value on the goodness of fit, it should be higher. And there it is right there. There is, so the p-values can be seen right here where it says prob, the p-value prob, or p-value, which they both just said p-value. P-values are probabilities, and with this right here, we would still believe it's normal. And so you can see the differences right here where this is a quintessential example of the distribution is mostly unimodal, kind of symmetric. It is very unimodal, mostly symmetric. And the normal probability plot follows the straight line, and the goodness of fit test comes back. Both of them, there's two here, two statisticians or two pairs of statisticians, Shapiro-Wilk and Anderson-Darling. Those are the names of the statisticians who made these types of goodness of fit tests. Both of them converge to normality via the ways in which they're checking it because the p-values are greater than 0.05. And that's the keynote. If you're wondering what do you need to know from this, a goodness of fit test used to check normality. Well, if it has a high p-value, we still believe the data is normal. Let me repeat that. A goodness of fit test used to check normality will believe the data is still normal if the p-value is high. A goodness of fit test that comes back rejecting normality. Here we go. This is a good one for that. Look at it. Normal probability plot's bent. Histogram is very right skew. And the p-values are very low, rejecting normality. So that is kind of how checking normality works. I'm going to call this section checking normality. And that covers a good bit. Covered skew, covered goodness of fit test, covered normal probability plots. So we covered a lot in that part of the review. So now we get to the questions that really just destroy people. People just have no idea how to look at this. We have to know what you're looking at. And we always say, let me mark this, we say draw it out. So chapter 5, review, normal curve. You have to take the information right here and draw on it to make sure you know what you're doing. Let's grab everything right here and bring it over to this screen and check it out. Okay, it says the middle 60%, and that's what's been shaded in on the curve. So once I see the middle 60% right here, immediately, I'm not supposed to be able to draw up there. The middle 60% is this. That's the middle 60%. If that's the middle 60%, if anyone's in the chat, feel free to answer. But what is total outside? And then what is one of those arrows worth? So the total outside would be 40% because 60% inside, 40 outside. Now be careful, it's not 68 because it doesn't go between 1 and -1. This graphic's showing different z-scores. Nice job, Jad. We'll throw Jad some points right there. Great work, Jad. You're right, this is 20% here, and this is 20% here. Now the question asks us, what is the 80th percentile of body temperatures? Now, what's the context of it? Well, what does 80% mean? 80th percentile means 80% of the data is where? I'll answer in a moment, but Jad, thank you so much. 80th percentile means 80% of the data is where? So you have to be like, okay, what does 80th percentile mean? So what does 80th percentile mean? That means what? Below that point. So we would say, wait a minute, the 80th percentile is going to be right here because 80% of the data is below that point. You can see 60% and plus 20% is 80%. So then the question becomes, what is this point right there? And that's what this point is. But what is that? What is that? That is the what for this point. And I'm not highlighting one right there. I'm highlighting exactly right in there, that spot. What is that? That's the what for this point, because it gives the context there. And I'll start putting the actual numbers from the distribution. We see right here it has a mean of this and a standard deviation of this. So we put 98.2, 98.9, and that's good enough. Because now we can, what is that 0.842, Jad? Do you know? Morning, Noel. What is 0.842? Does anyone know what 0.842 is? Because if we know that, we should be able to solve this. We're really close. You can also probably guess at this and probably get it right from here. Does anyone want to guess what the body temperature is of the 80th percentile? What do you think? Remember, it's body temperatures. It's like, what is your temperature? Like when you take your temperature. So when you answer this, think you're answering like a temperature that a human would have. So don't worry if you get it wrong, but be like, it's asking a temperature a human has, and it's a higher temperature. Well, it's not too high. It's 80th percentile. The mean is 98.2. That is the area above. So 20% is above this point. 20% is below this point. 60% is between. So the 60% is the between right here. That's the 60% between, leaving 20% outside. And then what is this? Where is that? What does this value mean right here? So I've color coded that. That means something too. What does that value right there mean? That value is at 0.842. I have to sneeze. No, I don't. What does that mean? That'll be the key to solving it. Like, what is this? We're so close. Casey, you got it. It's a z-score. Well, how can we use that? Do you have any guesses at the answer and how can we use this? I want you to get these connections and be like, that's a z-score. Z-score tells us how many standard deviations something is above or below the mean. So how could we use that? You're right there. Also, you can guess at the answer and maybe get it right. Well, not 84% below. That means this is the z-score. So this is the z-score because it comes from the 0, 1 curve. So you see right here, this is 0, this is 1. That's where z is equal to 0.842. So that is the z-score. And good answers, Noel, right there. Keep up the answers. So how are we going to use the z-score? We're right there at the answer. Also, does anyone have a guess at the answer? Because it wants the body temperature of the 84th percentile. So we want the body temperature right here. You could just take a guess and you might get it. Not even kidding. If you take a guess, you could be like, man, it's about this. Any guesses at the body temperature? Remember, it's a body temperature. Like whenever you take these guesses, be like, I'm guessing a body temperature. Don't worry about being wrong or anything. Just take guesses. I'll answer it here in about 10 seconds. But be careful. Good answers. Good guess. So we're looking for some number between here and here. We threw some points out. So we're looking for a number between here and here. And you can kind of see where it's at. So try again real quick. So the 80th. I think that is good enough. Well, how can we use the z-score? And good guess Parker and good guess Noel. I think Noel, your answer would do it, and Parker, that's close. So how can we use the z-score? Okay, this is the last thing I have to ask you, and then I'm going to solve it, or someone can do it in the chat too. A z-score means what? How many watts something is where? What does a z-score mean? Let's write both formulas that we know. We have the original formula with the z-score, that a z-score is equal to, and we know the z-score, observation minus mean over standard deviation. We can also, how many standard deviations is above or below the mean? Great answers, Noel. And then we can also use it to say, rework the formula and say the observation is equal to the mean plus the z-score times the standard deviation. That's just a reworking of the formula. Like all you're doing is solving for y, and you're also basically stating what the z-score is, that it's how many standard deviations something is above or below the mean, because look, here's the mean, and how many standard deviations something is above or below the mean. So with that, we plug in our numbers right here, and we get that the mean of 98.2 plus the z-score of 0.842 times the standard deviation of 0.7. And this information is found up here when you look at the original data of the mean and the standard deviation. So this equation right here solves for the z-score. A z-score is how many standard deviations an observation is above or below the mean. And then this equation is working the equation to solve for y. If you were to go right here, you could take and times both sides by sigma and get z sigma equals y minus mu. So you could rework the equation to this, and then you could go right here and add the mean, and you could get mu plus z sigma equals y. Does that make sense? Like if you go and follow these paths right here, you can times both sides by sigma to put sigma on top of the equation, and then you can add right there. So if you see the reworking of the equation, you're just taking this original equation and bringing it through these steps to turn it into the other one. So that's the reworked equation to solve for y. So z equals y minus mu over sigma can be reworked to solve for y, where mu plus z sigma is equal to y. Does that make sense, Noel? And this is the answer right here. And I'm not even kidding. 98.7, I think we'll do it. How can we tell we need to use the, if you're solving for y? If it says like, what is the observation? Yay, Kiana, good to see you there. And yes, and if I mispronounce anyone's names, please let me know. Kenia, I think. Kenia, yes, it will be the same. I was like, let me double check. I'm so blind. Kenia, we're throwing some points. It is basically the same. And once again, because we give the exams all through Proctorio and ask those questions, we're solving some chapter 5. This question was one of the normal curve questions. Good to have you here. I look and I'm like, I got look at that. 98, and I think it accepts 98.7, so that was a good enough guess. 98.7. There we go. Which of the following is a bivariate display of quantitative data? A, B, C, or D? Let's take a vote right now in the chat. We're going to start a poll on A, B, C, or D. Take a vote and let's see what you say. So you need to know each one of these and be able to draw a little drawing of these. Which of these is bivariate quantitative? So glad we got people swinging about it. I love it. It's not even Wacky Wednesdays. What are you doing, Crash? he's just being crazy. We have 100% of the right answers right there. It is a scatter plot. So I have this graphic right here that you should know. It shows you the different combinations. If they're blue, they're quantitative. The middle of it is bivariate quantitative, because quantitative. This is bivariate categorical, because if you go to the left all the way, you have to go all the way to the left. At the very top of it is the univariate graphics, like you can make a pie chart of your favorite bars and a bar chart of your favorite pies. So once again, I'll disappear. Let me disappear. Keen Eye. Thank you. Yeah, I'm making a mod too. Someone's going on limbs here. Keen Eye. Thank you so much. There we go. Awesome. I appreciate that. So you should be able to draw a little mini drawing of each one of these. A scatter plot is going to be something like height, weight. You mentioned the exam is similar to Canvas content. Yep. Does that mean it's multiple choice? Multiple choice, number input, true, false. Exactly. There's no written responses on this one, but there will be on the next ones. This is a scatter plot of height, weight, and both variables are quantitative. A histogram is uni or bivariate? Is a histogram uni or bivariate? A histogram. Is a histogram, which would just be like height. Notice how we'll highlight the ones that are... It's uni. A histogram is univariate. Great job, Parker, too. And Noel. So it's univariate. Is a mosaic plot bivariate, or is it... Well, I'll do different colors for each one. Is a mosaic plot bivariate? We'll say, did you attend the Kahoot? Yes, no. Did you make an A or not an A? I hope it works out like this. Ooh, that'd be good. Is a mosaic plot univariate or bivariate? It is bivariate. Mosaic plots are bivariate categorical. They go with contingency tables. What do you notice immediately from this one? Great job, Casey, also. What do you notice about this mosaic plot? This is, did you attend the Kahoot and did you make an A? Now, the data doesn't always look like this, but did you attend the Kahoot? Did you make an A? People who attended the Kahoot, what? And you can see right here, and there were more people who attended the Kahoot via the marginal distribution. You can see the length of this is that there's more people attending the Kahoot than did not, which I always love. And then you can see people who attended the Kahoot within the conditional were what to the people who didn't attend the Kahoot. The people who attended the Kahoot did not. The people who attended the Kahoot were more likely to make an A. This one right here versus this one. This is within Kahoot attendance, yes. They were more likely to make an A than Kahoot attendance, no. This is fake data, but I'm always out there promoting the Kahoot. So there were also more people via the marginal that attended the Kahoot than those who did not. And let me know if you have questions. We're just kind of doing every one of these. No worries, it's practice. A bar chart, is it univariate? Is it bivariate? Is it cat? Is it quant? What is a bar chart? A bar chart, is it univariate? Is it bivariate? Is it cat? Is it quant? So a bar chart is what? Cat, dog, bunny. We ask people their favorite pet. What is a bar chart? It is categorical. Great job, Jack, right there. Categorical. And is it uni or bi? It's only univariate. Great job, Casey. Awesome. We're going to go limit Casey mod. It's univariate categorical. It's univariate categorical. And don't worry if you get anything wrong. Remember, you can make a bar chart your favorite pie and a pie chart your favorite bars. So that's a good way to memorize. Bars and pies go together. So you could make this same exact graphic right here as a pie chart. You could just draw this right here, and you'd have a little sliver for bunny, a bigger sliver for, so you'd have bunny right here, bunny, and then cat, and then dog. And so that would be the pie chart of it, and you can just convert it. It's just a different way to display the data. And then if you cut out the middle of it, you make it a ring chart or a donut chart. So ring or donut charts are just where the middle is cut out. It's just another way to display data. There's just different ways you can graph data and display it, and now that's a ring chart or a donut chart, just with the center cut out. So a really good question here also, just practicing what are the different types of charts. Scatter plots are bivariate quantitative, height and weight being displayed there, two quantitative variables. Histograms are univariate quantitative, that is just height being displayed. Mosaic plots are bivariate categorical, as in, did you make an A or not make an A, and did you attend the Kahoot? And bar charts are univariate categorical. Let's throw some points. Great questions. Here we go. We're going to do a few more chapter 5 really tough questions here and ask those questions if you have them. If the correlation R is close to 0, this implies there's no relationship. True or false? Here we'll say yes or no in the chat. So we'll start a poll again. Yes or no? If correlation is close to 0, this implies no relationship. True or false? If the correlation is close to 0, this implies no relationship. Ooh, people know their stuff. This is no relationship. Almost made a pattern, but then I didn't. Statisticians were like, oh, what? And frankly, I should maybe clean it up a little more there. And randomness. This has R close to 0. This is no correlation due to the R close to 0 and no association. But this, really, I started doing that recently. This, is this association strong, weak, non-existent, moderate? What is this association? Strong, weak, non-existent, or moderate? Is that strong, weak, non-existent, or moderate? Super strong. Great job, Preston, right there. No correlation, but strong association. The association can be done by drawing what the relationship looks like. So if you draw what it looks like and you see how tight it is, that's the strength. So all the points follow the parabolic form. Great job, Jack and Parker also. This one is no association because when you look at it right here, The no association can be seen because if you draw a line through, because it doesn't even have any form to it, or it's like if you give it the linear form, it doesn't have any linear strength because the points are spread out around it. The tightness around the form, which is the pattern the points follow, notice how that's a parabolic form and super tight, super strong. And then this one, even if you give it a parabolic form, which it doesn't have, it doesn't follow the parabolic form. It's all spread out around it. So that is the weakest possible relationship. That is a no relationship. No correlation can be found by drawing around it and seeing that it follows a zero pattern. So that's where the no correlation comes from. And then this one, if you draw around it like that, you do what's called a density ellipse. You also see it has no correlation. Correlation only measures what strength? So I guess we could do that too in here. Correlation only measures what strength? Correlation. Great job, Casey. You're welcome. Anytime. And this is recorded, so check it out later if you want. Lucas with those points. Correlation only measures what strength? Correlation only measures what strength? Which you can see how I drew that there and this there, which the first condition of correlation, or the first three, is QQ straight enough, no outliers. So correlation only measures what strength? And that does it for this review. Correlation only measures, which that R is the value of correlation. Correlation only measures what strength? QQ straight enough. No outliers, because outliers do anything to correlation. Correlation only measures what strength? Linear, you got it. I'll put Canvas content review. How about this? Ooh, you got to watch this. You ready? Outliers can make a weak correlation strong. What do you think? Tell me the answers to questions 1 through 5. How many of them are true? How many of them are true? Anything is possible! Yes. All of them. When it comes to correlation, outliers can do anything. So all of these are true, but how about this? I'll be really nice. Okay. Which of these are false? How many of these are false? Which of these are false? So now it's trickier. So to review, nice job. Preston's on fire with those answers. Preston, really good job. Kayla, good to see you. And Kayla, you're basically there. Good answers. And Preston and Kayla, 2 great answers are throwing even more points. And good morning, Kayla. Good morning, everyone right there. So if you see outliers and correlation, that has to be true. So good memorization technique is outliers can do anything to correlation. We have the condition QQ straight enough, no outliers. So if we say outliers can do something to correlation, it's true. That's why we don't want them in correlation, because it'll dictate the correlation. So outliers and correlation has to be true. Now you get down to why do we use certain measures of center and why do we use certain measures of spread? So if data is skewed, what is the proper measure of center? And what is the proper measure of spread? If data is skewed, which that's normal. If data is skewed, what is the proper measure of center? What's the proper measure of spread if data is skewed? Median and IQR respectively. Median for center and IQR for spread. And that's because those are resistant to outliers. So these right here, where we have median and IQR, this is false right here. Let me change the color. The reason we use median and IQR is because they're not impacted by outliers. So we don't want to use mean and standard deviation because they would be impacted by outliers. Because think about this. with a data set that's very small, 1, 9, 90. What is the median? What is the median? What is the median? What's the median? It's 9. What's the median now? What's the median now? You're like, wait. What's the median now? What's the median now? What's the median now? So notice, and great job, Jack, Noel, Kayla, everyone right there, Preston, is that I'm making this more of an outlier, and it's not changing the median. And the small data set here might change the IQR, but bigger data sets, you're fine. But what is dramatically changing? Great job, Andrew, right there. As I add more zeros to this, this would be dramatically inflating the what? As I add more zeros to this, this would be dramatically inflating the what? That would be dramatically inflating. It is making a huge outlier, and outliers can dramatically impact the mean. And then you might say, well, why would it impact the standard deviation? The mean is known as y bar, and the standard deviation is known as S. And let's look at the standard deviation formula. The standard deviation formula, which you don't have to memorize, is the sum of the squared difference right here from the mean. So when you look at this formula, and it is square rooted, that would be variance. If not, what is used to calculate the standard deviation? When you calculate standard deviation S, what is used to calculate standard deviation S? What is used in the calculation of the standard deviation? Someone might already say it right there. You can say it again. When you calculate standard deviation, it's how much do things standardly deviate from the what? Because this is the observation's difference from the what? Standard deviation is literally a metric of standard deviation from the mean. So think about this. If outliers impact the mean, then they impact the standard deviation. So both of these right here are impacted by outliers. So data should be normal, unimodal, symmetric when using mean and standard deviation. And when data is skewed, we use median and IQR. So outliers can dramatically impact the mean and standard deviation. And that's why we do not like using mean and standard deviation when there is outliers. Does that make sense theoretically? Like, you can memorize, like, outliers do anything to correlation. It's true no matter what. Make strong correlation weak, weak correlation strong, and we could show some visuals on that too. But then understanding that the mean is when you average the numbers, if there's an extreme number. How many formulas we used on the exam? Really just the z-score formula, I think, is the only one, and the refiguring of it. We showed that earlier right here, the z-score formula. So you've got that formula right there in blue and this formula right there in green. And it's a reworking of the formula. So it's just a resolving. So if you know observation minus mean or standard deviation is a z-score, you can get the resolve of it, which is the observation is equal to the mean plus z times the standard deviation. Thank you, Noel. Good questions. And there's no formula sheet for this exam, but I do want to say this. And do we have another Canvas content that does the normal curve? Correlation is not affected by outliers. Someone help me out right here. This is false. Correlation is not affected by outliers. True or false? Correlation is not affected by outliers. Anything is possible! True or false? You gotta be careful because it's a negative. False. But it said it's always true, and it says correlation and outliers. No, correlation can do anything to outliers. That's the true statement. Correlation is not affected by outliers is false, and so be careful. You throw a not on there, and everything goes crazy. Scarpon. I want to do the other chapter 5 one on here, and please, if you have questions, ask them. We can jump around, do other things, jump around in the room. I'm gonna try to find that other. We've done those. Sure. Who can get this one within seconds? What % of runners do you expect to be above 31 minutes? This is a good one. What % of runners do you expect to be above 31 minutes? Does anyone know it like that? And then I'll show you how to get it. And please slow me down if I go too quick. I've been working these problems so long. And when I do want to state this about this problem, if you see on this problem the following, great job, Preston, that is correct. We'll show you how to get it. If you see this on the problem, you need to use the empirical rule. Use this. You need to use this. So, and great job, Noel. It's 2 standard deviations. So between Preston and Noel, you can see the solve right here. That what we do is we draw our normal curve. And then at the center of the curve, we put the mean of 25. And the standard deviation is going to be 3. So I'd immediately start drawing. And we go to 28, 31. You can actually stop right there and you can put your z-scores below. And then you do what? How much area is this? Now you've got numbers right here. How much area is this right here? How much area have I drawn right there? We need above 31. So above 31. 95, yep. Notice how we stopped here at 2, and between 2 and negative 2 is going to be 95% of the data, so that's 95%. And then we go right here and we do the outside, and if 95 is inside, what's total outside? 95 inside, total outside is what? Do total first, and then we'll cut it in half. Because you have to do 100% of the curve. You have to be like 95 inside, this outside, and then I'll cut it in half for you. Or you might cut it in half before I can, which Preston already has the answer, so. 2.5 either side, exactly. 2.5 here, 2.5 here. Do my famous riding the rail trick where you got this dude up here and he rides it and he goes, whee! And when he rides the rails right there, he should get 100% of the data. So you check your answers by going across here and making sure all the answers add up to 100% if you've done it properly. So we have done it properly. The answer is 2.5% according to the empirical rule. Really good question, and please slow me down. I've done a lot of these, but I know everyone comes in at different places. This one literally just asks you the z-score. So what is the formula for when it says, what is the z-score? You think, I need to solve what? So once again, we're looking at how to solve these. If the question says, find the z-score, you say, you know, I need to do a certain formula. Question says, solve the z-score. So you say, what is my z-score formula again? Because it was greater than. It said above, right? It says like, what percent of runners, and thank you for asking, Noel. It says what percent of runners are above 31 minutes. Above would be to the right of it. Took longer, above. So what percent? And Raptor, good to see you there, Reptar. What percent of runners are above? Since it says above, it's 2.5. If it said we're quicker or below, so if it said below, it'd be 97.5, or it said it's in the what percentile, which races are kind of weird because you can think of percentiles almost reversed. I wouldn't put percentile in this question, but it'd be 97.5% are below and 2.5% are above. Yes, if it said below, if it said what percent of runners are faster, that'd be quicker times. Or if it said what percent of runners are below, then it'd be to the left of it. So below would be to the left right here, and then above would be longer than. So if it's above, it's to the right, like longer times at the race. Good question. So calculate the z-score. What do? Help me with a formula. Because once you give me the formula, I can solve it pretty quick. So it says calculate the z-score. What is the z-score formula? A z-score tells us how many standard deviations an observation is above or below the mean. So use that information that the z-score is how many standard... Exactly. So we have right here a z-score is equal to the observation, which you can also just call it x. A lot of formulas say x. I prefer to call it y for some reason. Just the way I learned to do it. And Preston's already got the answer, it looks like. And then we do the mean, which is mu, and then the standard deviation, which is sigma. Mu meaning mean and sigma meaning standard deviation. Just listen to the alliteration. Mu, mean, sigma, standard deviation. These are also the population parameters versus y bar, sample mean, and s, sample standard deviation. Just different ways of doing the notation depending on the context of the data. So we go right here and we say, well, what is the observation? My box of candy weighed 452. That's how much my box of candy weighed. We have right here, the distribution is normally distributed with a mean. There's the mean. And then we have that it also has a standard deviation of 17.1 grams. So the standard deviation right here, plug the numbers in, and we get 452. And great job, Preston. I was looking to see if it was negative right there. And we just take and do this. And notice our observation is below the mean, which means we're down here somewhere at like between -3 and -2 standard deviations below the mean. So the answer is -2.51. And make sure it seems reasonable to you when you put in this answer right here. You have to be like, okay, is that below the mean? Yes, it is. That's what a negative z-score would show us. So we're 2.51 standard deviations below the mean. Here's the crazy part. Do you know what percent of the curve would be below this? I want you to see, it's scary how long I've been doing this. What percent of the curve would be below this? Does anyone know? It's a new question. Probably about 0.007. To do this, we wouldn't give you this on the test, but we go to the applet. And when we go to the applet right here, you should know what the picture looks like. And I know it's very little to none of the curve. So MuBot's going to drop the applet in the chat right here. And you should have a drawing. Do you see my little tiny little sketch of a drawing? What you should be able to do is make that sketch. And now you could put in below and go to z-score and go to negative 2.51 and round to the third decimal. And I was off by a thousandth. Oh no! But does my little tiny sketch right there look like that over there? Does my little tiny quick sketch look like that over there? That's what I want you to see about this. Yes or no in the chat. I just want you to acknowledge. I mean, I know I did really bad. I just drew it really, really quick, but does it kind of look like I did the below and I'm like, it's about 0.007. And I was close-ish, because I know a lot of numbers on the empirical rule and a lot of numbers beyond the empirical rule. So I was able to get within a thousandths of the answer, knowing some numbers. It was close to 2.5758. I love the normal curve. It's good stuff. I need a shirt that says, I love the normal curve. Very close. Thank you, Noel, right there. Well, we need to know how to calculate the percentage of on that are nope. Preston, good answer. All 3,500 points. Nope. You would need to know that this area is less than what? Here's what you would need to know on the test. On the test, you would need to know that this answer is somewhere between how much and how much area. Let's show this and show what you would need to know on the test. Mubot given a lot of points. This area has to be between somewhere between what area and what area. So use the empirical rule. And this area has to be between how much area and how much area. So we're pretending that this is a test question now and what you would need to know at the empirical rule. Boom! Wow! That is worth a... That's right. Great answers. That is exactly right, because using the empirical rule, 95% right here and 99.7%, meaning this is 2.5, and that's also 2.5 on the other side. So 2.5 is too much, as in if you went below here, there's 2.5, but that's too much. And then this is 0.15%, and this is 0.15%, but this is too little. So it's more than 0.15, but less than the 2.5. So that is exactly what you would need to know on the test. Like, you should be able to deduce that. You wouldn't have to know within my answer that it was 0.7, I guess 0.7, but it was actually 0.6%. You would, if we gave you plausible answers, anything contained in that range, we wouldn't give you two answers. We would give you like this answer right here and then something like 3%, which you could also look at it visually, just depending on how good your drawing is. But 3% is not plausible because 3% would have to be more than 2.5, which that is not. Does that make sense how test questions can give you like 3% that can't be? Multiple choice, true, false, numeric entry, good questions. It'll look just like the what. Put it in the chat for 500 points. What will the exam look like? And we'll put a hint on the screen right over here. What will the exam look like? Canvas content. Yep. So there's a numeric entry on the Canvas content. Correlation is not affected by outliers. We know this one. This one is definitely false.
Wow.
Wow. Wow. I wanted this one.
Another one.
Correlation close to zero implies that there's no relationship. We did this one earlier. So once again, we showed where there are relationships, but correlation is close to zero. So another false. David, good to see you there. A strong relationship can have a correlation of zero. True or false? Yes or no? I want you to type yes or no in the chat or do the poll. A strong relationship can have a correlation of zero. Yes or no? A strong relationship can have a correlation of zero. A strong relationship. No, that's fine. Don't worry. Throw you some points right there. I think I owe some points. Now be careful. We see 50-50 in the votes. What do you see on this bottom row right here? This bottom row shows you a what? What does that show you right there? That is showing you right there a what? It is a parabolic, curved, nonlinear relationship. It's nonlinear. Easiest way to call it. But it's definitely a what relationship? See, it has correlation of 0 because it's not linear. But look at what I've shown here. It's strong. So can a strong relationship have a correlation of 0? Yes or no in the chat? True or false? A strong relationship can have a correlation of 0. And we see it on the bottom row right here. Very true. The tightness of it around the parabolic form. But it's nonlinear. It doesn't have a strong linear relationship, so it has a correlation of 0. This one is a no correlation, no association. No association. So a strong relationship can have a correlation of 0. Much like this one right here, if there is a correlation close to 0, this implies there is no relationship. That is false. So in order to have a correlation, it has to be correct. QQ straighten up. No outliers. Plot doesn't thicken. Oh, that's regression coming up. But it needs to be a straight relationship. So it has to have a straight, like the points have to follow a straight line. If they don't, it can still be an association. It would just not be a correlation. So count 10. We'll do one more of these. Is there any chapter people want to review? We could also do chapter 5. We've almost done... I don't think we did all this one. No, we didn't do this one yet. Oh, Parker knows. Mod right there. Parker in the chat. Parker, I hope you're doing well. Thank you. Let's throw 1,000 points for Parker showing up. Parker, a Stat 201 legend, a true legend right there in the chat. Good to see you, Parker. It makes me smile when I see, like, former students. I'm like, hey, sometimes people come by from like 5-6 years ago, and I'm like, I think I know you. Can we do where we find the in-between? Yeah, we'll do this one, and then we'll do one of those. Noel, you got it. So this one says, we're looking at body temperatures again. W. Parker, what do you think I should add to this curve? What extra could I add down here on the bottom? It might help us. It might not. I think it might not help us, but let's add it in. What could we add in? W. Parker. What else could I add? Mean standard deviation with the z-scores. So I always like adding my z-scores. Great job, Preston knows right there. We're going to add in some z-scores. Second monitor during our nice. It is, and I want to say the biggest thing that I love. One thing I love is when students come back by and recruit students. So Parker, if your work ever wants to come and recruit like UT students, you're welcome to. Swing by, check out the new YouTube office. Did we ever meet in person, Parker? Because I was in Texas. So, and say, hey. So what percent of adults have a body temperature higher than 99.26? This question's easier than you think. Where is 99.26 is between a z-score of 1 and what? Look at this curve and tell me 99.26 is between a z-score of what and what? This question's easier than you think. 1 and 2. So we are looking for how much is this area? Because the curve says 99.26 right here. This down here, which I guess is not important, so I'm going to put in black, is 97.14. We're interested in that one. Like, what percent of adults have a body temperature higher than this? So we want temperatures higher than that. Yeah, I don't think we did either. Yeah, well, if you're around, say hey. So it's telling us that this is 13% of the area total is the amount of area total. But we don't want this answer. We don't want 13%. So that's 13%. So what is that area, which is the area above 99.26? Not 5.5. Good. You're kind of close. Preston has, small math there maybe. Because how did we get that? Because we know that the total area is 13. And then if you look at it, you can double check it for symmetry, but it is symmetric. So how did we get that? Preston, you're right. And Jake right there is right. It's 6. And in the middle is 87%. No, wait. That's right. Like, it doesn't matter that it is. Not 16 minus, and that not 16 minus 2.5. Good guesses, good guesses. So if these areas total are 13, you could cut the area in what? Because if you look over here, we could take this and bring this over here and show it's the exact same size. So we go over here and do a little rotate, and you notice how it's the same size right here? So you see how this is the same size over here as that? Exactly. Nice job. People are seeing it. Does that make sense? See how it's the same thing? It's the total is 13%. Correct, Madeline. And Madeline, we'll throw you some points right there. So notice on this question right here, it gives you a normal curve picture. And on this question right here, how would you know to use the empirical rule on this question right here? So look at the difference between this question. I'm gonna zoom in really close. Look at the difference on this question right here and the one we just did. So do you see the big key difference between these two? Let me put them side by side so you can see. Zoom out. So on the one on the left, it says use the empirical rule. So when you see a question that says use the empirical rule, you will use the empirical rule. So if you see this right here, you will use the empirical rule. So use that right there. Use that if you see it, and great job. And then if you see just like a drawing right here where it has like a picture, you will use said picture and said information from the picture to help answer the picture. So when you see use the empirical rule, you're 100% using the empirical rule. Good questions. So the questions will dictate use the empirical rule. Let's do a between one. And once again, here, let's do a big chapter 5 review. We're gonna switch Canvas content because we've had that up on the thing for a while. And let's do more chapter 5. Okay. True or false? The normal curve and z-scores can be used properly for all data. True or false? The normal curve and z-scores can be used properly for all data. True or false? True or false? The normal curve and z-scores can be used properly for all data. The 13 was given to us. Really good question right there. The 13 was part of the question. And that question I asked is false. 13% is given right here, saying that the total area is 13% outside of it. The outside shaded area is 13%. And that is false. It would have to be unimodal and symmetric, which normal means unimodal. So it'd have to be unimodal symmetric, which is normal. Great answers, Preston. So to properly use the normal curve, we need unimodal, one peak to it, and symmetric folded over. So good answers right there. And that unimodal symmetric means normal. So now we go over here. I'm going to make a graphic. And we're going to say test scores are normally distributed with a mean of 70 and a standard deviation of 10. And we're going to ask, what was the score of the students who got in the 98th percentile? So don't use the applet to get the answer, but I want the score of the students who got in the 98th percentile. Okay, and I already know the answer looking at this graphic. Okay. So let me repeat the question again. Test scores were normally distributed with a mean of 70 and a standard deviation of 10. What are the scores of the students in the 98th percentile? What does 98th percentile mean? What does 98th percentile mean? And you're on the right. I see where you're going with that. What does 98th percentile mean? 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 Well, not that they made above a 98. Remember, percentile means what? The top 2%. Kenai, great job. Yes, the top 2%. You are correct. So now we look at our graphic and we ask ourselves, what do we see right here? We have the what shaded in on this graphic. Currently shaded in on this graphic is the what. So go ahead and read the graphic, know what the graphic's showing you, and then be able to draw. Yes, no, that is correct. Great answers. So what do we see on this graphic? How will I use this information to help me out? Especially that. 96% of the data, which that's true. So what else could I then figure out from this? If this is 96%, then what could I know next? 2% on either side. So wait a minute. Remember, we're looking for the 98th percentile. So what do you think about this point right here? Like, tell me about this point. Nice job, Parker. Seen it too. Below that line is what? Below that line is what? Below that line is what? 98% of the data, right? And all you're doing to get 98% is you're adding up these numbers here. Does that make sense? You're adding up those numbers. So below that line is 98% of the data because it's the top 2% also. So you can see above this line is 2% of the data. And we're just going like above where that's at is 2% of the data. Exactly, Matt. Does it make sense? Like visually what you're seeing right here, that is the 98th percentile because it's the top 2%. 98% of the data is below there. So we have confirmed that this is the 98th percentile of the data. And so then the question becomes, well, what other information do we have right here? And this graphic makes it super clear what this is. What do we have right here and what do we know? So what else do we know? Look at the rest of the information given to us. And what else do we know? What else do you know? What is that? What is 2.05? So you have to think, what are these down here? What are those? What is 2.05? Yes, Preston, go ahead and do it. Also, if you 2.05 technically 2.05. Because also look at this. If you go here on this graphic and do the following, you can pretty much guess the answer. If you put the mean of 70 and start going up, you can see that the answer is what? So you can kind of guess the answer if you put this, because it says, what is the score? Does anyone have a guess of the answer? I think Preston might literally, yep, Preston, I look up and Preston's got it. So Preston has the answer, and Preston said the answer is, the observation is 90.5. So we know the z-score, and we're going to go ahead and solve this. Nice job, Preston. Let's throw Preston some 500 points. Put some W's in the chat for Preston. Really good work, Preston, because we can go right here and do the observation is equal to the mean plus the z-score times the standard deviation. And so we would have 90.5, we've already kind of solved it, is equal to the mean of 70 plus the z-score of 2.05. And then we go right here and do times the standard deviation of 10. Does that make sense? You can also kind of see it visually, as we were saying, to see that weight 2 standard deviations up is 90, and that's the 98th percentile. I know I'm saying 90 a lot, but the 98th percentile is 90. And great job, Parker, right there. W. Preston, Loco, good to see you there. Looks like some Tom and Jerry. And there's 100 right there. So you know it has to be just a tiny bit above 90. But good question. I know how to mark this. You can see it visually. That's just the tiniest above 90. Can you go back to how you got 90.5? Yep. So we know right now the what. What is the graphic gives us the what? The graphic currently gives us the what up there, way up top. And I'll start highlighting. Up top, the graphic gives us the what? The graphic gives us the what? What does the graphic give us? The graphic gives us the what? Not the standard deviation. Well, the question gives the standard deviation. The graphic gives the what? The graphic gives the what? Not quite the percentiles. I mean, it kind of does. There's a lot. This value right up here is actually the what, though. I mean, it says it right there. I mean, everyone's saying things. Let me throw some more points. You're saying things are basically correct. That number up there is the what? Like it says it right there. And then you can tell because it's on a 0-1 curve. Mean of 0, standard deviation of 1 is the standard normal. Everything on the standard normals are what's? Everything on the standard normals are what's? Z-scores, yep. So the z-score tells us how many standard deviations something is above or below the mean. Remember, the z-score tells us how many standard deviations something is above or below the mean. So all we do is plug in the mean, the z-score, and the standard deviation. And also you can kind of tell visually. Does that make sense? You need to plug into the formula. I've got it all color-coded right now, where you would take, we figured out where the 98th percentile was. So we knew we were looking for this spot on the curve right here. That has a z-score of 2.05. plugging in the z-score of 2.05 times the standard deviation of 10, which I should have highlighted that right there. There's the standard deviation, but it should be all color-coded for you to see. Please let me know if you have questions, though. The more you see these, the better you get. And Preston, let me ask you, Preston, have you solved a lot of these and have they gotten a lot easier? And do you draw them out? Feel free to comment, Preston. We'll get another one going here because I feel like people really kind of like these questions are kind of tricky. So I've asked what the 15th percentile was. And so we could do that. Here's a trickier one. And we're going to ask what the 15th percentile is on this curve. So we're going to ask what the 15th percentile is for this curve. And so get ready. I'm going to change the question. We're going to ask what the 15th percentile is on this curve. So we're going to ask what the 15th percentile is. So we're going to have a drawing right here. We're going to say, what is the 15th percentile? So this is another type of question right here. And it's what's the 15th percentile? Test scores were normally distributed with a mean of 800 and a standard what was the 15th percent? Now, here's where I know all the IQ results, all those things, right? 15th percentile has to be where to the what? So this is theory that we need to know. The 15th percentile has to be where to the what? So help me out right here. The 15th percentile has to be where to the what? The 15th percentile has to be where to the what? When you hear 15th percentile, it has to be where to the what? So you know 15th percentile has to be where to the what? Oh my gosh, knocking over my phone. 15th percentile below the mean. Because 15th percentile is on the lower side of the curve. So we see the what right now. The 15th percentile, great job, Jake and Noel right there. So what do you think? It's Jack, actually. What do you think? If we know the 85th percentile, nice job, Christopher. Good to see you here. Christopher knows. If we have the 85th percentile, that means 15% is above here and 85% is below here. We have the wrong side, right? So what do you think we could do with this information right here to find out the other side of the curve? What do you think we could do with that 1.04 to find out the other side of the curve? Where do you think the 15th percentile is at? You got it. There it is right there. It's just the negative version. It's the other side of the curve. Does that make sense? So we have the upper 15. We want the lower 15. And notice how it's just the negative. Great job, Clay, right there. You're right. So if we know that this is at 1.04 for the top 15%, then this would be at negative 1.04 for the bottom 15%. Does that make sense what we deduced there? It's like, well, the top 15% is at the z-score of this. The bottom 15% would just be on the other side, and Preston's got the answer. Yep, I like using 100 because then it's easier to do the standard deviation, but Preston is correct. Also notice, so with what, and great job, Parker and Preston. Yep, that is correct. If you go here and start writing the numbers, you can see that the answer has to be a little bit what to what. So start writing your numbers in because we know the answer we're trying to find is right here. Your answer needs to be a little bit what to what. So start thinking about my answer has to be a little bit what to what. And then you'd be like, oh, that's how they got that answer. Knoxville. I gotta stop Reddit from posting. So say something crazy on there. The answer has to be a little bit what to what. Your answer needs to be a little bit what to what. Between 600 and 700 and closer, great job, Noel, right there, closer to 700, right? So if you notice 696 meets that criteria that it's a little bit below 700. So what is this number right here? It's a z-score. Notice I already wrote z, just the opposite side. I kind of like it when it does that sometimes. The opposite side of the curve on the z. So we write the formula again that the observation is equal to the mean plus the z times the standard deviation. We start plugging in our numbers right here that we have the mean of 800 We have the z-score of negative. Is there a range? Yeah, we give a range. Yeah, there's a little plus or minus on it sometimes, and we're slightly forgiving, but just try to get them right. And then if you feel like it was mean to you, let me know. So we'll go here. I'm putting in the numbers. I forgot to write them, and so I could color code them. And then means gonna be bigger. Gotta write small. 800 plus the z of negative 1.04 times the 100, and that is equal to 696. There we go. With the exam, maybe not. It'd probably go 695 to. I mean, we might even do an exact answer. Like, you don't usually want to guess it. Great job, Loco, right there. Nice answers. That is correct. You don't really want to be guessing it. So this is 800. Like, you don't want to like take a pure guess. You can get them by pure guessing, but this one we might put in 696 or maybe 695 to 697. It just depends. There are leeways on some questions, but if you solve it, it's like 50-ish questions. Good question, like 50-ish. What chapter do you want to do? We have 45 more minutes. I might even grab some Red Bull before class. We started early today. Let's head to the main screen, but tell me what to do next. This is your office hours, your time. This is our time down here, so your time is our time. It's one of those times. What should we do? Chapter 1 is knowing your variables. Chapter 2 is knowing how to describe univariate data, whether it be categorical or quantitative. Chapter 3 is going to be bivariate categorical. Chapter 4 is comparing distributions. Chapter 5 is normal curve. And Chapter 6 is correlation. And then pivot tables, which is only like 4 questions. Variables. Do some variables. Variables. So Chapter 1, Noel? Chapter 1. Here we go. Let's go check it out. Nope. Excuse me. Okay. How many types of variables are there? How many types of variables are there? Yeah, we'll do pivots next. You got it. How many types of variables are there? I might even bring up notes for this. How many types of variables are there? There's kind of 3. I say 3 sometimes. There's really categorical. There can be like pictures and stuff. Usually categorical, quantitative. And here's a huge thing. Ordinal variables are categorical. They're not quantitative. So if you see ordinal quantitative variable, that is false, false, false. I can't state this enough, that if you see an ordinal quantitative variable, that is what? Say it in the chat with me. If you see ordinal quantitative, like ordinal quantitative, you go, no. No. That's false. That is false. There's no ordinal quantitative. It's ordinal categorical. And put in order from least to greatest, false, false, false. Ordinal quantitative is false. Not that I'm literally telling you what's on the test. And then there's nominal. So a categorical variable puts things in groups. Like, what state are you born in? What's your favorite state preference? Great job, Noel, right there. Those are categorical variables. What's your class level? If you go to ordinal, ordinal is going to be, has inherent order to it. As in, military rank goes from like private, sergeant, second lieutenant, first lieutenant, captain, something like that. It goes in order. Also, things like class level, freshman, sophomore, junior, senior. And then favorite bar, if you make a pie chart of it too, right, is going to be nominal, because there's no inherent order to this. No inherent order. You wouldn't say like, oh, it goes cool beans and then half barrel and then barcade. No, there's no inherent order. Like, steak preference goes from rare, midwell, midwell, or whoops, rare, mid-rare, midwell, well, and then hockey puck higher, or blue rare even below. So ordinal categorical variables are groups that have inherent order, like they're put in an order that is inherently set up to go from like freshman, sophomore, junior, senior, like it goes in an order. Ordinal variables, ordered variables in groups, and nominal has no order to it. No, nominal. Nominal. Call it nominal. Or like state born in. Just because you can alphabetize things doesn't make it not ordinal. State born in is nominal, doesn't have inherent order. Quantitative is actual real numbers. They must be numbers. Categorical can also be put as numbers, and I will say this, there is the special case, which is identifier. Cannot / will not repeat, and that's a huge way to know it's an identifier if it can never repeat structurally and identifies individuals or identifies observations. It's the point of an identifier, is to identify. Actual real numbers can have, they can be discrete, which is whole numbers. Oh, we should put, well, we put what they are, cannot, will not repeat. That's what they also do. This would be like your TNID number, license plate number. Things like that are generally identifiers because they identify your car, they identify you at school. Discrete numbers are whole numbers, like pizzas you order. You order 1, 2, 3 pizzas. You don't order half a pizza usually. Maybe some places do that. But then continuous, will this be the semester? Nope, I'll never know how to spell that. Can have decimals. Are all those? Yes, these are all below categorical. Bingo. Continuous is going to be things like, continuous would be like pizzas you eat, which can be like 1.5 pizzas. I ate 1.5 pizzas, but I ordered 2 pizzas. Does that make sense on the different types of variables right here? These are like subtypes within. The real big 2 types of variable are quantitative or categorical. And then all of these are basically subtypes within. Like the ordinal variable is a subtype of categorical. The nominal is a subtype. Like you can say it's nominal categorical. And then identifier is a special case categorical variable that cannot, will not repeat. Discrete are quantitative variables that have whole numbers. Like if you say how many pets do you own, how many surgeries did your pets get? They must be discrete. You don't get half a surgery or own half a pet. You don't order half a pizza. Maybe you do, but I don't. And then continuous can have decimals. It's just the number format can have decimals. Any questions on this? This was a huge, quick, fast review. Before we start the test, do we need to show Proctorio that we have? No, you don't. You could show us a little bit. The better. Still have class, you bet. Always have class. I get paid to teach. I get paid to be here. So they pay me to be here. Let's see right here. Could you figure out? I want you to look at this data, and I want you to tell me what kind of data do we have right here. So in the chat right now, what you're going to do, and here I'm going to do this. I'm going to make oh, no, actually, it's right. Okay, this is tricky. We're going to take a look at this data. I'm going to deselect the row first. Deselect. There we go. Okay. And I want you to take a moment right here, and I want you to type into the chat what these are. So your task is to start typing like I, C, or Q. For I for identifier, C for categorical, Q. So you need to start typing in I, C, or Q. And you need to do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So what is it? Digimon, digital monsters? No, Pokemon. So you gotta do a lot of these. Start right here, and then tell me, is that I, C, or Q? Go next one, I, C, or Q. 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 C being categorical, Q being quantitative, and I being identifier. Is that I, C, or Q? 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 So give me a moment, I'll let 1 or 2 people answer. Don't worry about being wrong. Just give it a try, and then we'll check some answers. Once again, when you see us checking the answers, I'm going to show you how to do it. And woo, okay, let's see. Christopher's got some answers. Let's throw some points right there. Any more answers in the chat? Thank you, Christopher. Let's throw Christopher 500 points. Oh, hey. Clay's got some answers. Okay. If something is an identifier, it cannot what? If something is an identifier, it cannot what? Something is an identifier, it cannot what? Cannot repeat. So you know what? Let's look at the data. You ready? Don't worry if you got it wrong. Don't worry if you got it wrong. Number, this is quantitative. You can tell it's quantitative. These are all. What's I get it. Yeah. What's the? Do you know what the identifier is? The identifier is actually what of the Pokemon? What is the identifier? Don't worry, a lot of people got it wrong. I don't think anyone got perfect answers yet. Not number. Number repeats. I know that sounds crazy, but Charizard can be Charizard Mega Y, Charizard can be Charizard Mega X. So that's what you got going on, Venusaur Mega and stuff like that. So the number of the Pokemon, Venusaur Mega is still, so the identifier is going to be that. And this right here, it's kind of, the number, you could probably go quantitative because you can talk about how many Pokemon are between. Like there's this many Pokemon, like this is the first Pokemon released, the second Pokemon. I don't love that one as a question, but I could argue it's a category, like you could almost argue this is the category of Charizards. Does that make sense? But it's a time order release. It has a time element to it. Stupid Gen 6 ruining our database integrity with megas or something. Number isn't an identifier, you said during the Kahoot. Yep, exactly. Keen Eye got it right there. Exactly. It's not, and so we did this one during the Kahoot too. And then type is going to be what? Which I think a lot of people got that. I think I see pretty much all right answers. Actually, pretty much everyone got the rest. Those are all categorical. The only things that can be quantitative are going to be numbers. Generation could also be argued to make categorical, but you can say how many generations are between. So generation is actually, people put, it's going to be Q for generation quantitative because you can talk about how many generations are between. So this is what I would go with right here. Quantitative for, you can also make it categorical. You can what's called discretize it. But this is where you're representing a number because it's like Gen 1, Gen 2, Gen 3, and you can say like, oh, this is 2 generations later. And if the math makes sense. But think about this, if we do something like gender, and we have, my gender is 1 and my wife's gender is 0, so Chelsea has gender 0, Brian has gender 1. Do I have one more gender than Chelsea? Yes or no, do I have one more gender than Chelsea? Chelsea has gender 0, Brian has gender 1. Do I have one more gender? It's just representing a group. Does that make sense? It's just this has been represented male and female represented that way, where I don't have one more gender though. So, but if you think about from Gen 1 to Gen 2 of Pokemon, is there a difference of 1 that makes logical sense right here? If we say Gen 1 versus Gen 2, does it make sense to say that this is 1 gen later? Like 1 gen higher, whereas opposed to 1 gender higher. Remember, like Brian's gender is 1 higher than Chelsea. That doesn't make sense, but this is 1 gen later or 1 gen higher. Yes. So that means it's quantitative. Does that make sense why this is quantitative? That generation of Pokemon, if you say like there is a difference of like this is 2 gens later, like, oh, you're in Gen 1, go 2 gens later. The 2 right here makes sense. But if I say, oh, add 1 gen to my gender, you don't add 1 to gender. You can say go 2 gens later. It makes more sense to talk about generations of Pokemon in terms of a quantity of what generation are we at. It's a little tricky right here. Generation could also be used as categorical, and I have used it as categorical. It's just you can what's called discretize things. So a lot of things we can do. I think, once again, the big trick right here that I do like is that number is not an identifier, name is the identifier. And once again, if you're saying something's an identifier, you need to look at what? And don't worry if you got caught by this. So it's nominal because there isn't an inherent higher. No, Keen-Eye, great answer. Generation is ordinal because it goes from Gen 1 to Gen 2 to Gen 3 to Gen 4 to Gen 5 to Gen 6. If you treat it as categorical, you would say categorical ordinal. And numbers go in order inherently, so numbers are ordinal. But numbers, you don't really say they're ordinal, it's just they are because they're numbers, but you don't do ordinal quantitative. That's also a thing. So if you did categorical, this would be ordinal. And you can switch it. Like you can literally go here inside of jump and go over to the generation. And you see it's quantitative right now because it's blue. And you can go right here and make it ordinal. So now it's ordinal right there. And they split up nominal and ordinal. Continuous days have because, yeah. Keen-Eye, really good questions right there. Does that make sense? But I do want to highlight, if you are saying something is an identifier, you need to look that it does not what? Say it one more time for me. If you are saying something is an identifier, You need to make sure you look at it and it does not what? You have said something is an identifier. Yes, you need to go and look and be like, that repeats, that is not an identifier. So if it repeats anywhere, it is not an identifier, or if it could repeat. So before you mark identifier for something on the test, you'd be like, wait, that repeats right there. That's not an identifier. So identifiers cannot, will not repeat. They won't stop repeating, or they won't stop not repeating, because they can't repeat. What topic should we do next? That's pretty much a lot to do with variables right there. Also, I'm going to ask one more question right here as a true false in the chat. Let me do this. Once again, you've seen a lot of questions here. So random events must be... Okay. Random events must be equally likely. I think of a coin toss. Are you talking about the data set given because the names did not repeat? The names of the Pokemon did not repeat, and we answered this question right there. You got it. The names are actually not repeating. They are unique, and we can actually check that by going right here, and you can click this button, and you can see the max is 1 because it shows you. Good question. So the names actually are unique, like Venusaur, Venusaur Mega Venusaur, Charizard Mega Charizard X, Charizard Mega Charizard Y. They actually do not repeat questions. The names are the identifier. And we have about a 50-50. What is our classic example of when you think about random events and being equally likely? So here's 2 random events. Random event 1 is a coin toss. Random event 2, dice roll. Any number. And rolling 6. Lottery. So when you do a coin toss are actually, and great job David right there, good example in remembering that to be like, no, lottery's not 50-50, it's not equally likely. A coin toss is going to have heads or tails with a distribution of basically 50-50. So coin tosses are considered, just by the way we usually think of them, as equally likely. And rolling any number on a dice is actually 1/6 for all numbers, every number you get. But rolling a 6 on a dice has a what probability? It's not equally likely to roll a 6 or not a 6. Rolling a 6 versus not rolling a 6. So if we have rolling a 6 versus not rolling a 6, I'm just drawing the table of probabilities. Rolling a 6 versus not rolling a 6, what is the probability of rolling a 6 on a 6-sided dice? Rolling a 6 is what? I think there's 6 sides. What's the probability you roll a 6? 1/6. So while every number might have an even probability, the probability of rolling a 6 is 1/6. The probability of not rolling a 6 is 5/6. So if you think about, is it equally likely that I roll a 6 or not a 6? Because it's random events, whether I roll a 6 or not a 6. Notice how right here, these are not equally likely. So the probability of rolling a 6 and not a 6 are not equally likely. The probability of any number on a dice is equally likely, just like the probability of heads and tails are equally likely. And the lottery is our classic example. You either win the lottery or lose the lottery, and these are not equally likely. It's like 1 in a billion of winning and basically 100% lose. About equal to. It's pretty much you will lose about 100% of the time. Don't lottery play if you want, but you're just, yeah. Personal opinions with Brian. So random events are not always equally likely. Very true right there. And we oftentimes use simulations to show these things. Wrong, I won $2. Christopher right there breaking the odds, winning that $2 right there. And you could even put win something. So we could say like, what's the probability you win something? And we could change this now. Good answers, Christopher. I like that, Christopher. Thank you for that. I love those answers. Probability of winning something might be 20%, and the probability of lose might be 80%. Just win something now. So not win the jackpot, but the probability of win something might be 20%. The probability of lose might be 80%. We have to keep you hooked somehow. Braden, good to see you there. What should we do next? What chapter? We did a little chapter randomness right there. Random events don't have to be equally likely. Yeah. Drop those questions. Once again, do check out the review page. Got a lot of people doing reviews. What chapter should we do now? You pick. We do. Brian grabs drinks here soon. My wife message yet? battery mode turned off. Pivot. Let's do pivot. Okay, let's do some pivot. Chapter pivot. Review in the chat, and I do suggest this. If you're watching this review now, when test 2 comes around, start early. I send out a review sheet telling you what to review and on which days to review it. Some people use it, some people don't. It's all right if you don't, but it's better if you do little bits. Little bits. Okay, let's talk about pivot charts and pivot tables. Where's my Excel? Review in little bits. Little bits. Survey 10. Okay. Here we are. Oh, come on. Okay. So when you make a pivot table and pivot chart, remember to prospectively lotto playing stat students. Monomial distributions like it, Parker. Thank you, Parker. So pivot tables and pivot charts are used to display what two types of variables, but not really what variable. Finish my sentence, and you'll probably know some good stuff for the test. Pivot tables and pivot charts are used to display what types of variables, and you saw I just kind of did it, not that variable. Which that was a certain variable. Notice how it doesn't repeat. I don't want it though because I'm not going to include it, so you're already seeing me doing one of the questions possibly on the test where I don't want that included because I'm not going to use that. That was a what right there. Pivot tables and pivot charts are meant to display this variable and this variable. It can do either or, any which way you want, but we don't like to include this variable. Row number right here is the what of this data set. Categorical and quantitative is what we do display. Great job, David. And Marley, good answers, Marley. We don't display identifiers. Take those notes. Pivot tables can display categorical and quantitative. Cat, 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 quant, 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 cat, quant, 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 cat, quant. Notice how we do and don't do identifiers. To make a pivot table pivot chart, we're going to hit Control A, then we're going to go to Insert, and we're going to go to Pivot Table. Now, the number one thing you're going to put into a pivot table is going to be the values. The values are literally what you see. Like when I put GPA in here, I see GPA. There you go, there's GPA, the sum of the GPA. Now, the value field setting controls how you see this, whether it be min, max, whether it be average. Usually we do average. And we'll go right here and go to average. There's the average GPA of UT students. And I do want to state this once again, not trying to go too quickly, but I want you to see what you see in the tables, the values you see is found by doing the whats. The values in the table is where you put what in the fields. And it has a setting by which it's being displayed. The field, this is a field in area, it's just like it's like a square field, rectangular field, has a setting. And we are doing averages, and it's the value. Good answers, Braden, right there. That is the value you are seeing. So this is the value field. And the value field has a setting by which it displays, whether you do things like max right there and change it to the max GPA. So we're going to put this back to average for the value field setting so that we see the average GPA. I'm also going to make this nice and pretty right here by going to home and deleting decimals down to 2 decimals. Usually don't say to people my GPA is 3.148928942, whatever what I said right there, and just go to 2 decimals. Let's go right here and look at male versus female. There we go. Ooh, I did not help this out. What do you immediately notice about this pivot chart right here? And the rows and columns are how you slice and dice the data. As The Rock would say when it comes to rows and columns, it doesn't matter. It's just slicing and dicing and separating the data. But what do you notice about males and females right there? Let's go look at know what I'm gonna do? I'm gonna do something. What do you notice right there? Where's my sort data? I'm discretizing data. No one saw it? No one saw it? Uh-oh. Help me out. I'm going to say you're smart if you think you're smarter than 60% of students. Females had higher GPAs than male. That is true. Females had higher GPAs than male. And now I'm discretizing a variable, making it into groups, something you don't need to know how to do, but there we go. We have discretized a variable, and I don't think it's going to add that to, it didn't add it. So I have to do this again. I have to go to insert, pivot table, and do it again, and GPA is what we want to display, and we want to look at the average GPA, and then we zoom in here to make it big. We go to home, we delete decimals, and then we go here to the gender, and you can search up here, which is nice. Gender in rows, and then smart over here, which is a variable I made. Okay. And yeah, people who think they're smart generally have higher GPAs. You notice right here, we've got the do you think you're smart and do you not think you're smart, which I made right there. But I do want to say this, you could also go right here and say, you know, I really don't like those left-handed people. Where would handedness go if I'm going to say, I really want to limit my view and not see the left-handed people? What would we do with handedness? Whenever you finish what you're working on, I think my code's turning out weird. Yeah. Send me it on Discord. Yeah, and Evan knows filter. Nice job, Evan. And filter appears up here. We could be like, you know, those left-handed people, sorry, left-handed. We're just gonna remove you out right there. Oh, look, GPAs went up. Sorry, left-handed. I'm left. No, I'm kidding. Both my nephews are left-handed. I'm not. We love you left-handed people. But notice how what we've done right here is the values being displayed are what we see in the table. So that is the value being displayed. The rows and columns slice and dice where it doesn't matter.
It doesn't matter.
Which ones? No, Christopher, there are our favorites. You know what I think about that? This chart is, Christopher, because you said that, this chart is only left-handed people now. Look at those GPAs. I'm sorry. That is weird. You know what? Actually, we need to look at this now. We're removing out smart. We're taking away smart, and we're taking out handedness here, and then we're dropping handedness down here, and we're bringing back in. You can actually go here. What? That's crazy. What in the world? No, it's ambidextrous. I mean, of course they're smart. They can use both hands to write the same. Imagine you could write at the same time. You could write like the start of the sentence and the end of the sentence and just converge. We'll make that a quote of the day, Christopher, and then Evan, I might have to look at that later, but no, because good question is, Evan, send me the code, Evan. Send me the code, and I'll probably have to fix it. But really good stuff, Evan, and we'll make that a quote of the day. Christopher, nice stuff right there. Christopher, you've got quote 481. People are going to forever wondering what quote 481 is about. So quote 481 from Christopher right there. And then we can turn this into a pivot table pivot chart. We had a little bit of fun right here. We love everybody equally. Pivot table pivot chart of this. So there we go. I added some emphasis to it for fun. And you can really see, we could make the ambidextrous at the highest. You have to grab it right there. There we go. Oh, it didn't change it? Oh my gosh. OMG. There we go. There we go. And females, ooh, left-handed. Males are winning out with left-handed. There we go. Males are winning right there. Not winning, but you know. My left just peaked. Nice. Quick layout, add in the table, and then you can add the axis titles and all that good jazz. The axis title, primer, so there we go. And that's mostly all it is for pivot tables, pivot charts. Just make it look nice and pretty right there. Males, we're gonna be in a nice light purple. Light purple. Females, you can be, that's nice, I like that. That's cool. You can do outlines and all this stuff, you don't have to. More colors. Didn't want that. There's so much you can do. I like making graphics. It's like relaxing. I don't know if anyone else feels that way. It's just very chill. And you can just do it, and you can just say whatever. I'm just going to relax here and make my graphic. That's bad. There we go. Nice, neat graphic. Both my dad and brother is left-handed, and one is a what? And one's physicist and engineer. That's amazing. That's awesome. Both my nephews are left-handed. So, and also, it must be, I'm right-handed. And what's funny is my uncle was asking, he's like, Brian, you wear your ring on your own hand? I'm like, I'm mirror imaged here. So you see me doing this. I'm actually, that looks like my left hand, but it's my right hand because I'm mirror imaged on the screen. Famously, Ned Flanders in The Simpsons is left-handed. And I imagine it makes things a little bit tougher being left-handed. So once again, we're just having fun. We love left-handed people here. And once again, there's just, like, I'll tell you this much. I'm a right-handed male. My GPA, especially, oh, look at that. We're actually, sorry, right-handed males, we're actually the worst. So it's just data. It's averages among groups. It's a snapshot of one set of people. And once again, we love left-handed people. We love right-handed people. We love ambidextrous people. We sometimes just have a little bit of fun right here with the data. And technically, you should be starting these axes at 0, except Excel doesn't know that. I'll go right there and do that. Here we go. Not that big of differences. Probably not even statistically significant. I'm going to run that really quick, and then we'll do maybe 1 or 2 more things. I might grab a quick snack. But what we would actually do right here, if we really wanted to see if there's differences, is we'd go over to jump, and we'd do the following, and we would see if GPA can be explained by gender and handedness. We're even going to include their interaction. So, and then we'll include handedness over there. And so let's run this. And the answer is the differences are actually not statistical. It did come out with the model being significant, but the differences are not significant. And let me look at the full report. This is what we do. Effect screen. Where's the follow-up? I'll do factor profiler. Here you go. So you go male. See, look, and then there's the interactions. So there you can see it all, but the differences are not statistically significant. So are we able to do number 7? Yeah, let's do that. Yeah, let me pull that up. Yes, thank you so much, Evan, and I will get to that. I definitely will. Thank you so much. Evan, let's throw Evan 500 points. I discarded 3 different codes. My head is off center. If you get the chance, yep, I'll get it fixed up. Why are these not statistically significant? This is a question you need for your test. Why are these variables not statistically significant in this model? We haven't done models. Also, 320 should kind of know. Why are these variables right here in this model not statistically significant? Why are those variables within the model not statistically significant? There's a key number you should know. Why are these variables right here in this model not statistically significant? One more thing to look at. The p-values are not below 0.05. Great job, David, right there said it. David said the p-values are not below 0.05. The p-values are not below 0.05. I'm going to do one more analysis just because I love doing analysis. How many points for me to get a 100 on the exam? Unfortunately, the points don't matter here, but a good question. I could look into it a little bit. I could try to do something. And I'm just going to look at one more analysis on this, on comparing the means. This is 320/201 end of the semester, and on a significant difference. Yeah, there's no difference right here between left, right, and ambidextrous, and all the groups converge, all the confidence intervals converge. So all those things we were saying about left, right, ambidextrous, all the differences are likely due to. Well, in 201, and Evan, I will probably I'll try to do something. Remind me if you come to a bunch of the office hours, I'll try to make something happen with it. But your points right there, Braden, for 201 count. So they do count. Random chance, these differences right here are due to random chance. The intervals overlap. The connecting letters report shows that they're all the same group. Unless you go something, I'll show you this, and then we're going to do the last 2 questions. If we use gender to do GPA, you can actually see, I think, significant differences here when we do a compare the means with Tukey's on a significant difference. See how here you have male versus female difference, and it has group A, group B, showing a difference estimated to be about 0.223, which is statistically significant. So we do find a statistically significant difference between the GPAs of males and females of about 0.23 points. You can see the mean for females, the mean for males, and the connecting letter report shows A and B as groups, versus this connecting letters report shows A, and A, and the differences are likely due to random chance because they contain 0 as a possible difference. Hypothetically, what if you work with us partners the next quiz? Maybe. Evan, that's a good idea. That's a good idea. And we're going to do Noel's question right there. I kind of like that. We started a little 320, 201 crossover. And if you notice, the big number David mentioned right there was the 0.05 for statistical significance. You need to know that number in 201. That something is statistically significant when the p-value is below 0.05. I need to finish up your Kaggle competition to release it for Wednesday, and also the test. So next week will probably be a bit different because we have the test. So really good questions. And Noel, really good stuff here. I want to point to a few things. So let's do practice test review right here. So if you want to review the practice test, what should you look at? If you want to review the practice test review, go down here, and I will do a question right here in a second, but scroll down here to the practice test, and you'll see all the questions. I think they're all on here. So you can see a walkthrough of variable type. We did variable type a little bit earlier, and you can see I tell you what the identifier is, because it cannot, will not repeat. We got categorical, quantitative, and I go through, I try to highlight different things and show you each thing. I edited the videos, so that they look really nice, really clear, really easy to see what the answers are, and you see animations on each one. So let's go check out which question this is. This is chapter, or question 5, I think. Are we able to do number 7 and 5 on the exam review? Yeah, let's go do that pin message so I don't lose it. So here is question 5. Question 5 is right here. And so it says right here, a particular brand of batteries last 2.5 years on average with a standard deviation of this. Calculate the z-score that the battery lasts 2 years. So how are we going to get the z-score? Who knows how to get a z-score? Tell me the z-score formula in the chat. What is the z-score formula in the chat? I need the z-score formula. What is the z-score formula? Observation, z-score equals observation minus mean or standard deviation. Great job, Noel. And so what you see right here is we want the z-score of a battery that lasts 2 years, and that's the observation. Yep, thing minus mean or standard. Nice job, Christopher. And so z-score equals observation minus mean over standard deviation. And so that is going to equal 2.0 minus 2.5 over 0.32. I think is negative 1.56. Let's see what that is. So 2 minus 2.5 over 0.32, 2.56. Nice job, Noel. You got it. Notice it's below the mean because 2 is less than the mean. And now you have to go down here and it says, what percent of batteries would be expected to last 2 years or more? And I got this one wrong yesterday because I did 2 years or less. So we already have the what of this. We already have up there the what of this. Which you're just repeating back to me what we found. We've already found its what. Well, we do have the mean. You got it? Christopher's got it, it looks like. We already have its z-score. And with the z-score right there, we can plot greater than it. Well, the answer definitely looks to be more than what percent right now? The answer definitely looks, you got it, Christopher. Nice job, Christopher, 500 points. Yes, that's what we did. You're on the right track. So now think about this. What numbers do you know? Christopher's on the right track right here. So this area right here has to be more than what, but less than what? So it has to be more than that, but less than, more than this, but less than this. More than that, but less than this. See how the pink area right there? It's like more than this, if you shade all the way to the right of it, but less than this. Not quite good. Close, close, close. 68 is the area between here and here. We don't just want 68, we also want this. So think about how much area is this right here. Because 68, remember, is the area here. But we also want the area here. So this is 68. How much is over there? Because we want the total. That's 68. How much is over there? And it has to be more than this. Yep, you got it. Noel said it. So it's 84. And you can also figure out because 16% is less than here. So it has to be 84% above that line right there. So then how much, you can even do below and above on that. How much is the other, David's got it. This is 2.5 and this is 2.5. So you can just go the other side of these. Like you can just be like, well, over there has to be 84% then. And above this has to be 97.5. And you can also go through it to get 97.5. So it has to be between 84 and 97.5. Better yet, we can always go to the applet. I did not have this. I forgot. Yeah, no worries, Christopher. Just practice. It's just practice. These are, if you can get these, you're doing really well. Like these are tougher ones. And once again, a chapter 5 review question. And you can even go and check your answer to see that you basically got the right answer by going here. Oh, that's the, I went to review. Distribution, applet, normal. And then you go to find the percent. And we go -1.56. And there it is right there. And it is, or because we rounded the numbers. Yeah, oh, it's between 84 and 97.5. And that number is between 84 and 97.5. And now let's look at number 7. Seven. Ooh. High school football coach believes that the team's hours practice is related to the scores. So what do we do right here to check? What are the 3 conditions to check correlation? What are the 3 conditions to check correlation? What are the 3 conditions? Condition 1, Q. To make a scatter plot, both variables have to be quantitative. Straight enough is good, straight line is true. Do these points generally follow a straight line? Do the points generally follow a straight line? Are they generally straight enough? Shape, center, spread are the 3 ways to describe univariate data. The 3 conditions for correlation are QQ straight enough, no outliers. The 4 ways to describe bivariate quantitative is strength, direction, form, unusual features. So let me repeat that again. Univariate quantitative, which we're not dealing with right now, is shape, center, spread. Bivariate quantitative descriptors are strength, direction, form, unusual features. Those are the descriptors for it. We could describe this graphic with those terms. The 3 conditions, meaning things you must satisfy to do proper correlation, are QQ straight enough, no outliers. So it is 2 quantitative variables. It is straight enough, but the problem here is the big outlier. The big outlier is going to make the correlation weaker or stronger. The big outlier is going to take this correlation and make it weaker or stronger. So you ask, is it 2 quantitative variables? Yeah, it's quantitative. Weaker, because it pulls it out. Look, if we don't include the outlier, it's closer to a 1. Including the outlier extends out the density ellipse, making it weaker. We have an outlier for 40 plus exactly. So that's going to make it weaker because it expands out the bubble of the points. The tighter the points are around the line, the stronger it is, which is one of the ways to describe it. So that point is making it weaker, so removing it would bring the correlation closer to 1. So the only condition it doesn't meet is the outlier condition, and removing that would bring the correlation closer to 1. And do check out the videos on this. Once again, I've got videos going over each one of these. I'm going to grab a snack here real quick, or grab something. Until then, bye for now, everyone. Here we'll do our quick intro outro. Bye.